Bismillah ar-Rahman ar-Rahim. Today's lecture on Module 6 is about how to draw the free body diagram. In many engineering analysis process, free body diagram is a key thing to reach to the correct solution. Um, in order to analyze the structure, in order to find out the unknown forces, or especially in order to find out the external effects of applied forces, or for example, if given the material strength, you might be interested to find out at which particular load a structure will fail or a member will fail. In these particular cases, you might be interested to find out um, the external unknowns or the member strengths. So the first step in the analysis of structures, so whether it is civil engineering structure or mechanical engineering structure or any other structure, the first step in the analysis of those structures is to draw the correct free body diagram. So free body diagram is the diagram of the body of interest with all the applied loads as well as all the external effects showing on that free body diagram. And then you will perform some kind of equilibrium analysis to find out the unknown or the quantities of interest. Okay. So in today's lecture, we will primarily focus on first of all how to draw the free body diagram, and then in the coming lecture we will see that how can we then analyze the structure. But the first key step is to draw the correct free body diagram in the analysis of structures. Um but before learning the free body diagram, let's learn a couple of terms. So what is equilibrium of a body? So if a system of forces acting on a body keeps the body in a state of rest or in a state of uniform motion along a straight line, then that system of forces is said to be in equilibrium. Alternatively, mathematically, we can say that if the resultant of all the forces acting on a body are zero, so if the sum of forces acting on a body is zero, then that force system is said to be in equilibrium. And when I say sum of all the forces, so it means the forces as well as the moments. So sum of all the forces must be equal to zero, as well as sum of all the moments must be equal to zero in a body. If these two conditions prevail, so then mathematically I can say that that body or that force system is in equilibrium. Um, so for the equilibrium requirement is that the sum of all the forces in the horizontal direction must be equal to zero, sum of all the forces in the vertical direction must be equal to zero, and sum of the moments created by all the forces about certain point must also be equal to zero. So these are the three conditions. If these three conditions are satisfied, we will say that the body is in equilibrium. Please note that in the previous examples, in the previous lectures, whenever we were referring to summation of fx or summation fy, so, or summation of moment, so these summations implied the sum of external applied forces. Okay? So these summations implied the sum of applied forces. But from now on, whenever we will talk about sum of the forces, so these sum of forces not only include the applied forces but also their external effects, and their external effects are the reactions. So when I say sum of forces, so it means sum of all the applied loads and sum of all the sum of all the reaction forces. So similarly, sum of Fy means sum of all the applied forces in the vertical direction and sum of all the reaction forces in the vertical direction. Similarly, sum of moments means sum of the moments created by the applied forces and the sum of moments created by the reaction forces. And reaction forces, as you know, that they develop at the supports. Now, free body diagram is a sketch or a drawing of a body of interest separated from all interacting bodies. The term free implies that all the supports have been removed and replaced by forces or reactions that they exert on the body. So free body diagram includes all the information about the forces acting on a body and any significant geometry. So whenever you are drawing the free body diagram, you have to uh, separate out that body from all the surrounding bodies including the supports. And then, in order to mimic the response of those surrounding bodies and surrounding supports, you have to apply the corresponding forces or the reaction forces. Forces that act on a body can be divided into two general categories. So the forces can be the applied forces and they can be reactive forces. The effect of the applied forces, which are, I'm calling it as reactive forces, or simply I'll call them as reactions. Reactions are those forces that are exerted on a body by the supports to which it is attached. For example, if there is a beam and beam is supported by the wall, now if I apply certain load on the beam, so the beam will try to move down, right? And if the walls are strong enough, they will apply some kind of forces to the beam such that the beam should not come down, or the beam should not fall. So it means that the wall have provided some kind of forces to prevent the downward motion of the beam. So uh, the forces provided by the walls to the beam are kind of reaction forces, because those forces by the walls are developed due to the applied load on the beam. So the forces developed in the walls are called as reaction forces. So reaction forces are those forces that are exerted on a body by the supports, and applied forces are those forces which are applied on the body and not provided by the supports. And whenever we are talking about equilibrium, so we will say that the sum of all the forces means sum of the applied forces and the sum of reaction forces must be equal to 0. And whenever we are drawing the free body diagram, both the applied forces and the reaction forces must be shown on the free body diagram. So what are the two key steps in drawing the free body diagram? The first step is to draw a sketch of the body of interest. So what जिस भी body का आप you want to draw the free body diagram, separate out that body from the surrounding, assuming that all the supports, surfaces of contact, supporting cables have been removed. So remove all the supporting bodies from that body and separate out that body of interest, and then draw the applied forces on that body, draw the reaction forces on that body, label those forces, also label the different distances. Um, if in the question it is said that you should not neglect the weight of the body, so you should consider then the weight of the body as a force as well, and which should be acting through the center of gravity. So these are the two key steps in drawing the free body diagram. The rest of the two steps concerns with the analysis of that free body diagram, which we will discuss in the coming lectures. Now, in order to understand the reaction forces, we must first of all understand what are the different types of supports that we may encounter in real world. The most difficult step to master in the construction of free body diagram is the determination of the support reactions. As a general rule, if translation of a body is prevented in a given direction, then the force developed on the body, then a force is developed on the body in that particular direction. For example, let's consider this beam which is supported by a roller support over here. Now, if I apply a horizontal force on this beam, the beam can move horizontally. It means that the support is not providing any kind of resistance to this body. So it means, or in other words, the support is not providing any reaction forces in the horizontal direction. But if I apply a force in the vertical direction on this beam, so the beam cannot move down. Why? Because there is a support over here and it is preventing its downward motion. Or in other words, I can say that the roller support is providing some kind of reaction force in the upward direction. So whenever I am applying a force in the downward direction, this support is providing a force in the upward direction to prevent the downward motion of this beam. So it means that I can replace this support with a force. So the behavior of this support can be mimicked by this force. So in order to draw the free body diagram of this beam, so I will remove the support and apply the corresponding reaction forces. And this type of support, which only prevents motion in one direction but allows the motion in other direction, is called as a roller support. Then there is another type of support which is called as pin support or hinge support. Let's look into this hinge support over here. So you can see that if I apply a force in the vertical direction on this bar, so this bar can rotate. Okay? It can rotate about this pin. So it means the rotation is possible. So there is no resistance is provided by the support to prevent that rotation. Now, if I apply a horizontal force on this bar, so this beam cannot move horizontally. It means that this pin support has provided some kind of reaction force to prevent that horizontal motion. So this I can represent that horizontal prevention of this support by a reaction force in the horizontal direction. Similarly, if I apply a vertical force, so the beam cannot move down, up and down, it means that the support has also provided a vertical reaction as well. So a pin support has the quality that it generates two types of reaction forces, one horizontal and one vertical. Then there is a third important type of support which is called as fixed support. Now let's consider this bar which is firmly attached to a wall or any other fixture. Now if I apply a vertical force, so this end cannot rotate. So it means that rotation is prevented. And when a rotation is prevented, it means a moment has been generated. So just like translation motion is prevented by a force, a rotation is prevented by a couple moment. So it means that this support, this fixed support can generate a couple moment. It can also not allow the horizontal motion. So it means a horizontal force can be developed. It is also not allowing vertical motion. So it means that this support can generate vertical force as well. So this fixed support has the quality that it can generate three types of three reaction forces: one couple moment, one horizontal force, and one vertical force. Let's look into some other types of boundary conditions. For example, let's consider that this body is supported by means of a cable, and this cable is then attached to some kind of a wall or any other fixed support. And let's say I'm interested to draw the free body diagram of this body. So it means, first of all, I have to draw the body and isolate it from the surroundings. Means I have to remove this cable from this body. In order to draw the free body diagram of this body, I have to draw this body and I have to remove all the supports which are attached to it. Like in this case, this cable is attached to this. Now when I am removing this support, I have to apply the corresponding reactions. Now these cables or ropes, they can only develop tensile forces, means they have um, the capacity to pull the bodies towards itself. Okay. So if I want to show the pulling action by the rope or by the cable on a rough page, what I'll do, for example, let's say this is a cable, and let's say this is that body. And now let's say I want to show the tensile forces. So in order to show that this rope is trying to pull the body, so it means that I have to apply a force in this particular direction. Similarly, in order to show that this rope is trying to pull the support, so I have to apply the force in this direction. So this is the that support wall or any other fixed support. So the tensile forces in a body, in a rope, can be shown with such that the arrowheads of the two forces are towards each other. So now if I'm drawing the free body diagram of this body, so I have to isolate this body and show the corresponding force. Like in this figure, I have shown the body and the corresponding force. And if somebody is asking me to draw the free body diagram of this wall, so what I'll do, I'll separate out this part of the body. So this is a support, and this is how the force will look like if I remove the cable from the wall. Let's look into another example. Let's say this body is supported by this surface which is inclined at an angle of theta. So if I am interested to draw the free body diagram of this part of the body, so I have to remove this surface to which it is supported. So first of all, I'll draw the body, and then if I'm removing this body, so I have to show the corresponding reaction force exerted by this surface on that body. So the reaction force will always be perpendicular to this surface. Okay, so the reaction force will always be perpendicular to this surface. So you have, if you remove this surface, you have to apply a reaction force which will be perpendicular to this surface. So this is the force, and this force is perpendicular to this surface. Let's take this example. So in the previous case, this surface was frictionless, so there was no horizontal forces developed. Now let's say in this case, this body is supported on a surface which is inclined at an angle theta, but this surface has certain friction as well. So it means that it also provides some kind of resistance to the motion of the body parallel to the surface as well. So there will be two unknown or two reaction forces. One reaction force which is parallel to the surface because of the friction force, and there is another force which will be perpendicular to this surface. So if I remove this surface, so I will have two forces which will be acting on that body. Let's consider this body which is also supported on a surface which is inclined at an angle theta. So this body is supported on this surface with the help of roller support, and you can imagine that this body can move up and down or along the surface. So it means that there is no reaction force or no restriction to its movement along the surface is provided. So only it is restricted to move in this particular direction. So there will be no reaction force parallel to the surface, but there will be only one reaction force perpendicular to the surface. So if I remove this surface, I will have one reaction force which will be perpendicular to the surface. Okay, this is a pin support which we already discussed. So if I remove the support, so I will get two reaction forces, one horizontal, one vertical. This is a body is attached to a fixed support. So if I am drawing the free body diagram of this body, so I will remove the fixed support and I will get three reaction forces, one horizontal, one vertical, and one couple moment. Now let's consider, for example, this body. So there is a bar which is connected to this support with the help of a link. So this link can be made up of aluminium, steel, bronze, copper, or any other material. But this link has the property that it can only take tensile forces or compressive forces. Or in other words, this link can only take forces along this member, okay? Along its own axis. This link can only take forces along its own member. So if I'm interested to draw the free body diagram of this bar, first of all, draw this bar. And now if I'm removing this link, so I have to apply the corresponding force. So I can apply a force in the direction of the link. This force can be away from the link, or away from this member, or this force can be towards the member. You can take both directions, okay? Because this is a link and it can take both tensile and compressive forces. So you can take any of the two directions and perform your analysis. But for the case of rope, please make it clear. For example, if this body is attached to a rope over here or a cable, so then I have told you that the rope can only take tensile forces, means the effect of the rope is to pull the body. So these will be the forces in the rope. So if I'm drawing the free body diagram of the bar, so I have to show the bar and this force. And if I'm drawing the free body diagram of the support, so I have to show the other part. So only this direction of the force is possible when this bar is attached to a cable, but this direction of force is not possible. Let's consider this case. For example, in this case, this bar is attached to another bar, and then this bar is attached to supports. And if I'm interested to draw the free body diagram of this bar, so first of all, I'll draw the bar, and then in order to mimic the response of this bar, I will apply a reaction force which will be perpendicular to this bar. Okay, so this is a reaction force, and this force is perpendicular to this bar. So this is the free body diagram of this bar. Again, you can choose any direction of the force. It can be towards the member, it can be away from the member. Similarly, for the previous cases, this Rx can be towards the member, it can be away from the member. Similarly, Ry can be towards the member or away from the member. Or in this case, this couple moment can be clockwise, or you can also assume it to be counterclockwise. So it will not change your end result after you perform the analysis. So it will not change the end result. Now, the next thing is that how these supports look like in reality. For example, how a roller support looks like in reality. So let's consider this steel beam which is attached to a concrete column or a wall. So in order to allow its horizontal movement along the axis of the beam, so the hole of the bolt is made slightly elongated. So the hole is slightly elongated. As a result, if there is some kind of horizontal forces, so the beam can move along its own axis. So this is how a roller support is usually made in the field. How fixed support is how fixed support looks like. For example, let's consider this pole, and this pole, steel pole, is let's say is welded with the steel plate, and this steel plate is then firmly connected to the concrete pier. So now this pole cannot rotate, it cannot move up and down, and it cannot move horizontally. So it means that we have provided some kind of fixed support. How can we provide a hinge support in a beam column connection in a building? So by connecting the middle portion of the beam to the column uh, will create a hinge kind of support, because the top and bottom portion of the beam are not connected to the column, and hence they can rotate. So rotation is possible in this beam, but horizontal movement and vertical movement is not possible. So it means that we have created a hinged beam. So these types of roller supports or hinge support you can also see in different bridges as well. So this is a pin support. As I've told you, that in order to connect the beam with the column using a hinge support, so you have to connect only the middle part of the beam, whereas top part and the bottom part of the beam are not connected to the column, and hence the beam can rotate. In order to make it a fixed ended connection, then you have to weld the top and bottom parts of the beam as well to the column, and hence not only the vertical and horizontal motion is prevented, but also the rotation is also prevented. So this is how you can provide a fixed connection of a beam with the column. In this figure, a pin support is shown in a steel girder railway bridge. So rotation is possible, but vertical and horizontal movement is not possible. The concrete beam column connection is always a kind of a fixed support. You can assume it in your analysis as a fixed support, because rotation as well as vertical and horizontal movement is not possible. In these figures, some of the roller supports are shown. For example, here you can see the roller supports. The rollers are provided over the bearing pads, so the beam can rotate about these rollers, as well as the beam has the capability to move horizontally along its own axis, but it cannot move down. So it's a kind of roller support. Here, a typical rocker support is provided, so the beam can rotate about this rocker support, but it cannot move horizontally and it cannot move vertically. So it's a kind of a rocker support or a pin-ended support. So these are some practical examples of how these three different types of supports look like in practice. Now let's come to the uh, topic of free body diagram. Any question till this point? Okay, so if there are no questions, so I will continue. So what are the tips to draw the correct free body diagram? So first of all, whether you are solving a numerical problem in mechanics of solid or engineering mechanics or in structural analysis courses, try to solve it neatly. And if you are drawing any figure, draw them neatly, because equilibrium equations directly come from that figure, that free body diagram. So it is very, very important that you draw it very neatly and correctly in order to get the correct equilibrium equation. And that is the only way you can get the correct solution of a problem. After drawing the correct figure and neat figure, label all the forces, all the angles and distances with values if known, or with symbols if they are unknowns. The support reaction must be consistent with the information presented in the previous slides. So you should know what type of reaction forces will develop if I remove a particular support. So whether it's a roller support or a hinge support, or it's a cable or it's a link. So you must know what type of reaction forces will develop if I remove that support. So let's consider the first example. Problem 6.1. The homogeneous 6-meter bar AB in figure is supported in the vertical plane by rollers at A and B and by a cable at point C. So this bar is supported by this surface and by this surface, and it is also supported by a cable. The cable is also attached at point C. The mass of the bar is 50 kilogram. Draw the free body diagram of the bar AB and determine the number of unknowns on the free body diagram. Now, in order to draw the free body diagram, I have to isolate the body of interest, which is the bar AB, from the surroundings. So I have to remove all types of supports from this body. So I have to isolate this body and remove all types of supports from this body. This is now that body. First of all, I have to show all the applied loads. There are no applied loads except the self weight of the body, which was 50 kilogram, and that weight must act through the center of gravity. So this is one force. If you can calculate it, so well and good. Otherwise, you can denote it with W. Okay? So if the values are known, write down the numerical value. If the values are not known, so write down the corresponding symbols or letters. Then at point A, there is a roller support. So it means that there is no reaction force in the horizontal direction. There will be only one vertical force. So remove this horizontal surface and apply a vertical force. Similarly, at point B, there is no force develops because it can move up and down, but it cannot move horizontally because of the wall. So remove that surface and apply a horizontal force over here. Now, as far as the cable is concerned, remove the cable. And as I've told you that the cable can only take tensile forces, and tensile forces in a cable are represented uh, with forces whose arrowheads points to each other. So if I want to draw the free body diagram of this bar, so I have to show this force on the bar. So if I remove the cable, I have to show this force on the cable to represent the behavior of the cable. So this is that tensile force. I represented it with T applied by the cable. So these are the forces which are acting, the total forces which are acting on the body. W is the applied force. T, RA, and RB are the reaction forces because they are produced due to the supports. So there are three unknowns in this problem: RA, RB, and T. Then W is known to us. And we can learn later that after applying the equilibrium conditions, we can find out these three unknowns. Now let's look into another problem, problem 6.2. It states that they draw the free body diagram of the foot lever. So this is a foot lever. Shown in the figure, the operator applies a vertical force to the pedal so that the spring is stretched 1.5 inches and the force on the link, this hydraulic cylinder at B, is 20 pounds. So it's a link, it's not hydraulic cylinder, it's a link. And the force on the link at B is 20 pounds. Assume that in order to produce 1 inch elongation in a spring, 20-pound force is required. So it means if this spring is elongated 1.5 inches, so it means the total force required to create 1.5 inch elongation is equals to 1.5 times 20. Okay, so now let's draw the free body diagram of this foot lever. So this is our body of interest. So let's call this point to be point O. So draw OAB body and then remove the corresponding supports from that body. So this is that body I'm interested in. So I'll show that body and isolate it from the surrounding bodies. Then this body is subjected to some force by the foot of a person in the vertical direction. Let's denote it with the force P, because I don't know what magnitude of force has been applied by the body. Then this body is attached to a hinge support over here. It is attached to a hinge support over here. So it will generate two reaction forces, one in the horizontal, one in the vertical direction. Then there is a spring, and spring has been elongated, and it means elongation. Whenever there is elongation, elongation takes place due to tensile forces, means the direction of the forces will be such that the arrowheads are pointing towards each other. Okay. So if I draw it over here to show the tensile forces, so this is how the forces in a spring looks like. So then I have to show the force on a spring which is acting on this body, and this force is equals to 20 times 1.5. So I have to show the numerical value, and then there is also some force in B, and this force is given in the question. It is equals to 20 pounds, and this is a link, and I have told you that whenever you are removing a link, so the force or reaction force in a link is always along its member, along the axis of the member. So show a force along the axis of the member. And in this case, you can also see that this link is stretched. So that's why I have shown a tensile force over here. So this is the complete free body diagram of this lever, showing the applied loads as well as the reaction forces. And in this case, we have two unknown forces, AX and AY, and also the applied load is also unknown. So three unknowns. Let's look into another problem, problem 6.3. Draw the free body diagram of the bar which has negligible thickness and smooth points of contact at A, B, and C. So this
और
is a bar.
क्वेश्चन
जी, please, question, please.
सर ये हम किस तरह मतलब हम जब पेपर में करेंगे पेज पे हम किस तरह इसका डायग्राम बनाएंगे सर जी आप नीट पेज पे आप शो करें सर जी
जी क्या शो करूं
सर ये जो डायग्राम है फ्री बॉडी
जी
डायग्राम
जी
तो हम
जी
किस
जी
तरह
जी जी
बनाएंगे सर जी हमें आइडिया
जी
नहीं
आप
समझ में आ रहा है सर
मैं चलिए देखिए इसी प्रॉब्लम को देख लेते हैं कैसे आप करेंगे ठीक है सो दिस इज द बॉडी ऑफ इंटरेस्ट जिसका आपको फ्री बॉडी डायग्राम बनाने को कहा गया है ठीक है सो व्हाट यू विल डू फर्स्ट ऑफ ऑल you will draw this body. This is the body, ठीक है OAB. Then it is subjected to some force by the foot, and this foot is mentioned in the question. It is applying a vertical force to the pedal. So then you have to apply the applied load on that pedal. Then there is a kind of a pin support at this end. So you have to show the corresponding reaction forces. One horizontal, doesn't matter whether it is pointing upward or downward, you have to show the forces. ठीक है, तो आप कोई भी फोर्स का डायरेक्शन अस्यूम कर सकते हैं, अपवर्ड भी अस्यूम कर सकते हैं, डाउनवर्ड भी अस्यूम कर सकते हैं, टुवर्ड्स द राइट भी अस्यूम कर सकते हैं, टुवर्ड्स द लेफ्ट भी अस्यूम कर सकते हैं. Then there is this spring. So when I am removing this, when I am not showing the spring on this body, I have to show the corresponding force. And I have told you in this slide that the spring is in tension. So this is the direction of the force in the spring. So I will show a force due to the spring. And then I will show the force due to the link. This force is applied load and it is not given in the question. So this is an unknown force. I'll call it P. These are the reaction forces on the supports. I will call them, let's say, Rx. And this is, I'll call it Ry. This is the force in the spring, and it is mentioned in the question that the spring is stretched by 1.5 inches. And it is also said it that in order to produce 1 inch elongation, a 20-pound force is required. So in order to produce 1.5 inch displacement, I need a force of 20 times 1.5. So this force is 20 times 1.5. So calculated, whatever value comes out, write down over here. And this force in the link is also given that, and the force on the link at B is 20 pounds. So this is also 20. So this is how you have to solve it. Okay. First of all, draw the body, then show the applied loads, and then keep on replacing the supports with the reaction forces. Let's look into another example and maybe it will be more clear. So let's take this bar, and this bar is supported by these two plates and supported at points A, B, and C. Now, in order to draw the free body diagram of this bar, first of all, and this bar is also subjected to some force of 10 pounds horizontally by the hand. So in order to draw the free body diagram of this bar, first of all, draw the bar. So this is the bar. Then apply the applied loads. So in this case, there is only one applied load of magnitude 10 pounds. So this is an applied load of 10 pounds. Then this bar is supported at point C. So since I'm removing the support at point C, so I have to apply a reaction force. And this reaction force must be perpendicular to the surface. So I'll apply a force perpendicular to the surface at point C. Then at point B, there are two surfaces. You can see that it is supported by a corner. So I have to apply a force which is in the middle of these two corners. So means at 45 degrees angle. Okay. So apply a force at point B. So remove the support at point B and apply a force. Then if I'm removing point A support, I have to again apply a force, corresponding force. And this force again will be at 45 degrees angles to the two surfaces. So this I can call it as RA. This I can call it RB. And I can call this force to be RC. So this is the free body diagram of this bar, in which I have shown the applied loads as well as the reaction forces. So this is what is also explained in the slides as well. And please do show the corresponding distances as well, if the distances are shown to you. Now let's look into another problem, problem 6.4. Draw the free body diagram of the dumpster D of the truck, which has a weight of 5,000 pounds and a center of gravity at G. So it has a weight of 5,000 pound, and this weight must act, as you know, must act through the center of gravity, and it must act downwards. It is supported by a pin support at point A. So there is a support at point A, which is a pin ended support. So it is also given to us, and a pin and connected hydraulic cylinder BC. So there is a hydraulic cylinder which is also supporting this this dumpster, and this hydraulic cylinder is also pin connected at this location and also at this particular location. Okay. So now let's draw the free body diagram of this dumpster. So first of all, isolate this dumpster and remove all the supports. What are the supports to this? The hydraulic cylinder and this pin ended connection at point A. So only draw this dumpster. Okay. Then show the applied force. In this case, the applied load is the total weight which is acting through the center of gravity of magnitude 5,000 pound. Then there is a pin support at point A. So you know that the pin support gives us two reactions, one horizontal, one vertical. So apply two forces in the horizontal and vertical direction. Name them Rx, Ry, or Ax, Ay. Then there is hydraulic cylinder. Hydraulic cylinder is also acting like a link. So if you are removing the hydraulic cylinder, so there will be a reaction force which will be along the axis of this hydraulic cylinder. So again, you can assume any direction. You can assume a force towards the member, or you can assume a force away from the member as well. So both is possible. So this is the free body diagram of this dumpster. Okay.
सर ये हाइड्रोलिक सिलेंडर के पास भी तो पिन सपोर्ट लगा हुआ है, तो इधर हॉरिजॉन्टल और वर्टिकल फोर्सेस नहीं होंगी?
जी मैं बता देता हूँ आपको, ठीक है। लेट्स लुक, चलिए इसी फिगर को देख लेते हैं। दोनों फिगर छोटी हैं लेकिन so I want to let's show the forces inside the cylinder, inside this link. ठीक है। If I am assuming that the cylinder, hydraulic cylinder or hydraulic link is taking a tensile load, so this will be the direction of forces inside the cylinder. ठीक है। So now if I am drawing the free body diagram of this dumpster, I will show this part of the forces. ठीक है। And if I am drawing the free body diagram of this truck, ठीक है, अगर मैं ट्रक का फ्री बॉडी डायग्राम ड्रॉ कर रहा हूं, so then I have to show the reaction provided by the supports. ठीक है। As you can see here that the pin ended support at point C is attached to the truck, whereas this hydraulic cylinder is attached firmly to the to this dumpster. So you don't have to show two reaction forces over here. ठीक है। Was this your question?
जी सर, क्लियर है, थैंक यू।
Problem 6.5, the floor crane and the driver have a total weight of 2,500 pound with the center of gravity at G. The crane is required to lift the 500 pound drum. So the crane has a self weight, this total crane has a self weight of 2,500 pounds, and it is also lifting, in addition to its self weight, it is also lifting a drum of 500 pounds. Draw the free body diagram of the crane. First of all, I have to draw the free body diagram of this complete crane, and then he is asking us, I draw another free body diagram of the boom, crane booms only. So draw the free body diagram of this part of the crane, assuming that this boom is of weight 300 pounds. Okay. So first of all, let's draw the free body diagram of this complete crane. So first of all, draw the crane in itself. So this is how I have shown the crane in itself. Now this crane is supported with the help of a wheel on certain road surface, and it means that this crane can move horizontally, so there will be no reaction force horizontally, but there will be only vertical force because vertical motion of the crane is prevented. Okay, so if I remove the earth surface, so I will get one reaction force over here. There is another wheel over here, so there is no horizontal force, but there is a surface over here at the bottom. So if I remove the surface at point B, I will get one another force. Then this crane is also supporting this drum of 500 pounds. So if I remove this drum over here, so I will get a force over here. Okay, and it is acting downwards of magnitude 500 pounds. So these are all the reaction forces. Then I have to show the applied forces. So the only applied force in this case is the total weight of the crane, including the weight of the person, which is 2500 pound, and it is acting through the center of gravity. And center of gravity is also shown in the figure. It's with the letter G. So the applied the weight of this crane acts through the center of gravity. So this is the free body diagram of this crane. So I have shown the applied load as well as the reaction forces. Now if I'm interested to draw the free body diagram of the crane's boom, so I have to take only this part. So what I'll do, first of all, I'll draw the boom. Then it is supporting this drum. So I will apply a load which is acting downwards of magnitude 500 pounds. Then this boom is connected to this part of the crane with the help of a pin support at this location at point C. So there will be two reaction forces. I can take any direction of these reaction forces. Let's say I am assuming these directions. Then it is also connected with the help uh, at point D with the help of a link, right? So the link is also providing a reaction force in the direction of the link. So I can take any direction for that force as well. So let's say I have taken a downward direction. Then this bar or this boom has a self weight as well, which acts through the center of gravity. Let's assume that this is the center of gravity. So this is the total weight, and the weight was given, it was 300 pounds. So this is the complete free body diagram of the crane's boom. It is also shown in the presentation slide as well. Okay. As I've told you, the only way to learn these things is to practice. So I will recommend you that after the class finishes, practice all the problems that I have solved in the class. And once you master it, so then there are additional problems as well that you can use for your practicing. Let's look at another problem, the last problem. 6.6, two smooth pipes. So they are frictionless pipes. Okay? So it means that, for example, if this pipe is connected to this pipe, so there will be no reaction generated parallel to the surface of the pipe. Similarly, this pipe is supported by the fork of this truck. So again, it's frictionless, so there will be no horizontal forces will develop at these contact surfaces of these 2 points. Only the vertical forces will develop. Two smooth pipes, each having a mass of 300 kilograms, are supported by the fork tines of the tractor. Draw the free body diagrams of each pipe, and then in the second part, draw the free body diagram of both pipes together. So this is the structure. So we have two pipes, and they are supported by the forks of a tractor. So first of all, let's say I'm interested to draw the free body diagram of this left pipe, pipe A. So first of all, I'll draw the pipe A, then I'll show the applied loads, and it is only subjected to its own self weight, which was of magnitude mass of 300 kilogram. You can convert it into weight by multiplying it with the acceleration due to gravity. So it will act through the center of this circle or cylinder. So this is the weight of this pipe. Then I have to remove this part of the fork. So I will get a force which will be perpendicular to this surface. Similarly, if I remove this part of the surface, I will get a force which will be perpendicular to this surface. So this is this pipe. This is the applied load or weight. This is one reaction force. Okay. I have to also remove this pipe as well. And when I remove this pipe, I have to apply a force which will be perpendicular to this to this contact surface. If these pipes were not frictionless, so there will also be a horizontal force as well. But since they are frictionless, so there will be no horizontal force in this case. Okay? So there will be only force perpendicular to the contact surface. If I'm interested to draw the free body diagram of pipe B, first of all draw the pipe B, then show the load or the applied load due to the weight which is acting downwards. If I remove the bottom surface, I'll get a force perpendicular to this. This is force P. And then this body is also connected to body A. So if I remove body A, I will get a force which will be perpendicular to the contact surface of the two bodies. So this is the force which will be perpendicular to the contact surface, and this is that force. Now in the next part, if I'm interested to draw the free body diagram of both of these two pipes, so let's draw the free body diagram of both of these two pipes together. So first of all, draw both pipes together. Then these pipes are subjected to its own self weight. So this is the self weight of pipe A, this is the self weight of pipe B. Then if I remove this surface, this fork from pipe B, I will get one reaction force. If I remove this surface from pipe A, I will get another reaction force. And if I remove this surface, so I will get another reaction force perpendicular to this surface. So these are the two or three unknown forces in this case. Okay. There is no vertical force or horizontal force at the contact surfaces of the two pipes. Why? Because I haven't removed uh, either pipe B or pipe A. Okay. In the previous cases, I removed pipe B, so that's why I got a force. In this case, I removed pipe A, so that's why I got the reaction force. In this case, I am not removing the pipe, so that's why I will not replace it with any force. So the force, reaction force, will only appear if I remove the support. If I am not removing the support, I will not get any reaction force. Okay? So reaction forces only comes in when I remove that support. Okay, so this was our today's lecture in which I explained how can you draw the free body diagrams. Practice a lot, because our coming lectures or most of our engineering mechanics course is based on free body diagrams. So please master this skill very well so that you can perform well in the coming lectures. In addition to the class exercises, I have also added a couple of more exercises as well, which you can try at home and try to draw the free body diagrams of these different examples to master it. Okay. So this is all from my side for today's lecture. If there are any other questions, please ask me.
सर ये प्रीवियस डायग्राम थोड़ा दिखाओ जो दोनों पे एक साथ रिएक्शन लग रहा है सर। प्रीवियस जो, हाँ सर, ये टेंशन जो रिएक्शन फोर्स, ये थर्ड एंगल किसके साथ बना रहा है सर? ये हमें कैसे किस तरह पता चलेगा इसका? ये थर्ड एंगल बना रहा है लेफ्ट साइड पे ए जो बॉडी है।
जी 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 जी
हाँ सर, ये
this is the angle which is made by the fork of the tractor with the horizontal. Okay. And if these two bodies are uh, let's say of the same size, okay, they are of the same size and they are at the same lying down on the same surface, so then the contact surface, the which is perpendicular to this surface, is also making an angle of the same angle. ठीक है. अगर ये दोनों बॉडीज जो हैं सेम डायमीटर की हैं, सेम रेडियस की हैं, तो फिर ये जो कॉन्टेक्ट सरफेस है इसके साथ जो परपेंडिकुलर आप ड्रॉ करेंगे, दैट विल मेक द सेम एंगल एज दिस फोर्क. ठीक है. इफ दीज टू बॉडीज आर ऑफ डिफरेंट डायमीटर्स, सो देन द एंगल वुड बी डिफरेंट, and then it must have been given to you in the question. But since these two pipes were of the same diameter, so that's why it was known to us that the perpendicular to the contact surface is making an angle of 30 degrees with the horizontal. The force will always be parallel to this. surface to which these two bodies are supported.
सर
जी
जो आपकी जो स्लाइड उसमें जो सारे प्रॉब्लम है सर उनकी सोल्यूशन कहाँ मिल सकते हैं?
उनके सोल्यूशन आप खुद करेंगे, ऑब्वियसली मेरे पास तो नहीं है।
अगर कंफर्म ना हो सर कोई
ठीक है,
क्वेश्चन
यू
हम कर
कैन,
ले और कंफर्म ना हो हम
हाँ, अगर आपको किसी क्वेश्चन में डाउट है, यू कैन ऑलवेज सेंड ए पिक्चर टू मी एंड आई विल कमेंट ऑन दैट। ठीक है, नो प्रॉब्लम इन दैट।
ओके
ठीक है, अगर आपको किसी क्वेश्चन में कोई डाउट हो रहा है कि इसका मैंने सही कैलकुलेट किया है नहीं किया है, सो आप उस पिक्चर का फ्री बॉडी डायग्राम मुझे सेंड कर दें, आई विल कमेंट ऑन दैट कि आपने सही किया है नहीं किया।
इसी क्लासरूम में
ठीक है,
शेयर
सोल्यूशन
करेंगे
मेरे
सर?
पास नहीं है, मैं क्लासरूम में शेयर कर दूंगा। अगर आप क्लासरूम में शेयर करें, हाँ क्लासरूम में शेयर कर दें तो दैट विल बी नाइस। ठीक है, एज ए कमेंट टू दिस लेक्चर नोट्स। ठीक है, जो मैंने मटेरियल अपलोड किया हुआ है लेक्चर मॉड्यूल 6 का, इसके कमेंट्स में जाके अपलोड कर दें या क्वेश्चन पोस्ट कर दें कि फलानी स्लाइड पे इस फिगर का फ्री बॉडी डायग्राम ज़रा बता दें, तो मैं उसको आंसर कर दूंगा।
हाँ सर एक और रिक्वेस्ट थी मेरी तरफ से।
जी जी
सर मैंने 2 क्लासेस की है क्योंकि मैं घर में तो वहाँ पर नेट काम नहीं कर रहा था। अभी मैं इसी हफ्ते में पेशावर आया हुआ, जो होमवर्क हुए सर पिछले लोगों ने सबमिट किया, मैंने वो सबमिट नहीं किए सर।
अच्छा, चलें,
तो
आप
क्या
होमवर्क
करूँ?
कर लें, होमवर्क करना ज़रूरी है। आप होमवर्क करके लेट सबमिटेड कर लें, फिर उसको बाद में देख लेंगे। ठीक है,
सही है सर, ओके सर।
लेकिन आप सबमिट कर लें, इवन इफ यू आर सबमिटिंग इट लेट, डू सबमिट इट।
सर किया है होमवर्क तो कल मैंने कंप्लीट किया, आज मैं सबमिट कर लूँगा सर।
बस ठीक है, कर लें।
थैंक यू।
ठीक है, okay guys, module 6 will not be included in the midterm, as you all know that your midterm is starting from next week. So prepare well for the midterm exam. All the course before module 6 is included in the midterm exam, and as you know that there are two modes of assessment. One, there will be a written kind of exam of 10 marks, and there will be a viva voce examination of 10 marks. So prepare well for the midterm exam, module 6, that the lecture that we studied today will not be included in the midterm exam. Okay? But for the rest, do prepare it well. How to find out the resultants of parallel forces, concurrent force system, non-concurrent force system, non-parallel force system, and how to calculate the magnitudes of the moment couple, how to convert a given force system into a force couple system, or how to convert a given force system into a single resultant force. So prepare these topics well. Okay? Exercise it and try to learn it more. Okay? If there are no more questions, so then I will wrap up my today's lecture so that you can practice it in the remaining hours for the exam, and practice more for numerical problems. ठीक है? I thank you all very much for coming, and let's see you uh, after the next week. So there will be no classes next week. There will be a midterm exam week. So after the exam week, we'll meet again. Thank you so much. Till then, Allah Hafiz.
सर सर
जी
सर
जी
कैन यू हियर? सर इस सब्जेक्ट में वाइवा किस तरह होगा? ये तो सारे न्यूमेरिकल स्टाफ है, तो मतलब आप किस तरह वाइवा पूछेंगे, जिस तरीके से हम फिर तैयारी करें सर?
बस आप देखिए, जो बेसिक कॉन्सेप्ट्स हैं वो मैं बताता रहा हूँ आपको,
सर ये
आपने वो
एग्जाम
याद
कैसे
रखने हैं।
होगा?
आपने अगर जी एग्जाम कैसे होगा, एग्जाम में बता दूंगा कैसे होगा, कोई मसला नहीं है। ठीक है, आप सिर्फ अपनी तैयारी पे फोकस रखें। आपने बेसिक कॉन्सेप्ट्स को अंडरस्टैंड करना है, और दूसरा, यू मस्ट नो कि प्रॉब्लम को सॉल्व कैसे करते हैं। ठीक है, एंड प्रॉब्लम को सॉल्व कैसे करते हैं ये आप तभी सीख सकते हैं जब आप खुद न्यूमेरिकल प्रॉब्लम्स जो हैं वो सॉल्व करेंगे। सो इफ़ यू आर सॉल्विंग योर होम असाइनमेंट्स एंड योर क्विजेज योरसेल्फ, so it means that you are good for the exam and you are good for the viva voce examination. तो कोई एक्स्ट्रा प्रिपरेशन की आपको जरूरत नहीं पड़ेगी। ठीक है, तो यही दो चीज़ें आपकी देखी जाएंगी वाइवा वोस एग्जामिनेशन में और रिटन एग्जाम में, कि आपके कॉन्सेप्ट्स कितने क्लियर हैं और आप प्रॉब्लम को सॉल्व कर सकते हैं कि नहीं कर सकते। ठीक है, सो आप सिर्फ अपनी
ठीक है
प्रिपरेशन
सर।
पे ध्यान। ठीक है, बाकी किस तरह वाइवा होगा वो फिर आपको वाइवे के दिन पता चल जाएगा। ठीक है,
और सर ये जो न्यूमेरिकल प्रॉब्लम्स आएंगी पेपर में, तो वो ये स्लाइड्स के ही होंगे कि नहीं, बाहर से कोई भी आ सकता है?
नहीं नहीं नहीं, वो कोई जनरल क्वेश्चन हो सकता है, कोई जनरल क्वेश्चन हो सकता है। जैसे क्विज में भी मैंने अपनी तरफ से बाज क्वेश्चन दे दिए थे अपनी तरफ से, तो कोई भी जेनेरिक क्वेश्चन हो सकता है, नॉट नेसेसरीली फ्रॉम द स्लाइड्स और फ्रॉम एनी बुक। आई कैन मेक अप ए प्रॉब्लम ऑफ माई सेल्फ एंड देन आई कैन गिव इट टू यू। ठीक है।
सर
ओके
टाइम
सर, थैंक यू।
कितना दिया होगा?
Time as time of the midterm paper as जो डिपार्टमेंट्स की जो पॉलिसी है या यूनिवर्सिटी की पॉलिसी है, द टाइम ऑफ सॉल्विंग मिड टर्म एग्जाम इज 1 वीक। ठीक है। So I hope best of luck for the midterm exam. I hope everyone will pass at least this time. Okay. So best of luck and prepare well. May God help all of us. And thank you so much and Allah Hafiz. And you may now sign off the Google this meeting. Everybody should sign off the meeting now.